Thank you very much for inviting me and a guy engineer from Intel, because I am the FPGA and the Xeon FPGA architect in the Intel site in Gdańsk. And I want to talk with you about the technology, what we want to provide, what we're providing to the our customers, and about the advantages of this technology for the parallel computing. What the Intel wants to achieve by the introducing the FPGA to the portfolio. The Intel is a CPU company. But we know that not everything can be done using the CPU, or probably can be, but not so efficient as the people want. So even when we have such impressive design like the Xeon, for the many groups of the customer, we see that would be possible to accelerate some workloads using the FPGA. Yesterday my colleague just told you about some circumstances, some problems what could be solved by the parallel computing by the using FPGA. And today I want to talk about the real product or the real design can help you to solve your problem. And also, what is very important, the Intel is a data center company, and our goal is not only to provide some FPGA solution, yes, which is the programmable, but also we are very interested in the deployment of the FPGAs and the use of these FPGAs in the cloud data center. I am a part in Intel as the data center group. And one of my biggest interests is not only to find some workloads for the FPGA, but also to help people use this FPGA in the natural environment for computing, like cloud. Yes. What we see, what challenges we see today as Intel in the data center? Yes. The important thing is that we know that some workloads could be computed or implemented in a different way. Yes, we could think about some universal way of the design, and, for example, have some trade-offs on the speed or some architecture of the hardware. Or we can make some more customized hardware which will work very efficiently with the software. Yes, we know that not every problem could be solved in the FPGA. Yes. Because we have some power constraints in the FPGA, we have the size constraints. Yes, even with the technology, which the Intel, we still are struggling with the physics. Yes, so I mean physics that with the nanometers. Yes, we couldn't go that down, but we are want to go on with the Moore laws that you probably heard about this one. Yes, but we see that not every problem we are able to solve using the CPU. Another problem what we want to solve is a power consumption. Today, designs like GPU consumes, it is very fast and is very well suited to the make a computation. But, for example, when you have the deployment of the 100,000 of the GPUs in the data center, so power consumption just growing up, and you must set up the electricity supply as close to your data center. Yes. What, for example, by the way, some of our customers are doing that. Yes. So. Another problem what we want to solve that we're providing the server, the Xeon server. Yes, the Xeon server is something what could be used for multiple reasons. Yes, for the computation and also for the handling, for example, some other workloads, for example, the web workloads. Yes. We know, for example, that some customers do not make, for example, HPC computation all the time. They also have some requests to make some other computation or to change the workloads in this one. So in our philosophy, yes, we have one server in the data center, but we want to have handling this for the multiple use cases, yes, because this is the cloud. In the cloud, you can compute everything, yes, and accelerate everything. What is an FPGA? This probably that people on this stage are the very know about the advantages of the FPGA, but I want to say why Intel FPGA. Yes, you know that Intel 2 years ago Intel acquired the company Altera. And today you are working very hard on introducing the Altera FPGAs to our Xeon. Yes, our product, and today the Intel has two products. Yes, one product is discrete FPGA. This is just nothing new. This is that just FPGA connected to the PCI Express. Yes. What is really, I'm working on the product which is called the MCP. This is called the multi-chip package, yes. When we have the Xeon processor and we have the medium-sized FPGA connected on the single die. What we are achieving that, using that approach? One thing, what we are achieving, we are connecting the FPGA as well, the FPGA can be handled, the workloads of the FPGA can be handled as memory very close to the FPGA. You can imagine that this is a single die, yes, this is a single silicon. And in the single, when we have our accelerator very closely connected, linked to the CPU, we can very fast move some workloads to the buses provided going from the CPU. Normally the QPI or the, now we are going the newest processor to the newest generation, which is called the UPI bus, to connecting the two processors, yes, together. Yes. In the same way, we can connecting the two processors and we can connect the FPGA as accelerator as we are on the QPI bus, this is the memory bus, internal memory bus, we are achieving the cache coherency. So the FPGA can be handling as the agent for the caching, because this is not just a physical memory, it could be, you can imagine this as the part of the cache. And also we are implementing the possibility to push data, for example, to read data directly from the CPU cache, and to push the data directly from the accelerator to the CPU cache, yes, without using the memory. Yes, we are using the normal addresses, yes, like the memory has, but the memory is not going to the memory blocks, but it is going directly to the cache. And in Intel processors, the best performance what you can achieve is that when your workload is able to avoid the accessing to memory. Yes, when you're because the access to the memory is very, very expensive. Yes. It is a reason why Intel processors has so big cache designs. Yes, and when we have the bigger cache, we can handling more data indication, we can handling the compute workloads even faster, yes. With the accelerator in the FPGA, we could a bit extending maybe not a cache, but we can limit the accesses to the memory, to the memory controller, by using that acceleration. Another problem that we are solving is bandwidth, yes, to the accelerator. Today we have the design when we can push to the FPGA the traffic about the 20 gigabytes per second, yes, not the gigabits, gigabytes per second, yes. In the next design we will have next year, we have the 40 gigabits per second, yes. It is a big bandwidth which we are able to generate, and we can feed accelerator with the data, yes. Also, that we are working on the design where we do not need the pinning of the memory in the CPU. Yes. Today, design, for example, for the RDMA, for GPU, it requires the pinning memory. Yes. As we are on the QPI bus, and we are using the QPI bus, we can avoid this, and we can use we will be able to use just a virtual space and also to use the virtual space in the safe environment, because we are providing here as part of this acceleration the IMMU engine, which makes help us to provide the security to the virtual machine. So in this model, you can even make the virtualization of the FPGA. So this is very important for the cloud. When, for example, we have the two customers working on the same server, and they want to use different workloads. Yes, it is why we introduce the virtualization concept as Intel. And now, how it looks like the programming. Yes, we have the two possible way to the programming. Yes, to the program and to the simulation. The first of all, before you can use, before you want to use the FPGA, you can try your design using the software simulators. It's completing the software, yes. You can write the RTL, you can compile this program, your RTL, to the our environment, what we call the IC. And with this IC, we can make the functional simulation of your RTL to get connected together with the software. In this model, in the pure software environment, you can check how your software can work directly with the FPGA, which will be created in the future. Yes. When the problem is solved, for example, it works for the simulation, you could use the Altera Quartus design and create the bit stream and push it to the real FPGA. Yes, when you are working on the platform, it is possible to just run exactly the same software to route to the simulator and the simulation to run there in FPGA. Yes, our job is to provide you that it will be consistent. Yes, but unfortunately not on the speed what the FPGA can provide. Another possibility is to use the BSP and to program your RTL in the OpenCL. Yes. In the OpenCL, you could make some simulation of the OpenCL, and also you can compile the OpenCL code to the RTL, to the Verilog, and run it on the Quartus and to push it to the FPGA. Yes, this is not the some interpreter inside of the FPGA like NIOS CPU, which performing this. From the OpenCL, we're creating the real RTL code. And we running this code on the FPGA. We have together to make possible that simulation. We are working on creating some software structure which could be used for the scientific workloads. The first of all, we have some standard user application, for example, like Cafe. And we provide to the CAF some machine layer. Yes? So your CAF application, your machine learning tools are not changed. you're just linking your application with our library, which is trying to accelerate some operation. For example, some computation of the floats, yes, like the colleagues earlier said, yes. And as a part of the, here's the example, what we're working and what we have currently solved, yes. We have the user application, and we have we are using the cafe. We have the machine layer for the MKL DNN, yes, which is that library which could be used in your cafe environment. And we are connecting this to the infrastructure. And thanks to this one, you could try to use this environment to handle. This is just example how you could connect the FPGA to your environment. This is, of course, one of the possible ways of doing that. That we can discuss it is that efficient or not. But it is that what we have for start for the developers. What we have, what problems, what we want to solve, yes. The first of all, we are working on the applications and the algorithms like that. We have the design for the CNN. We are working on design for the encryption, and we are very interested in some networking, solutions. Yes, because today our product is that. Sorry, our product is very young, and this is not deployed very widely. And currently, we as Intel, I'm as part of the Intel architecture, we are working on the finding a killer application for the FPGA, yes. Really, yes. It is funny, yes, we have a product, we have the idea, but we don't want that how to use this yet efficiently, yes. This is the sum, let's say, the request to you. Maybe you can help Intel to find a killer application. Yes, so that. Well, I can provide you some example. Yes, we work together with the University of Zurich, and University of Zurich just make implementation of the training for the machine learning. And we made the design, yes, because we have the two schools, yes, how to use the FPGA, yes. Some people say, okay, just provide the FPGA like a generic accelerator for something what is well doing by the CPU or the GPU. Or another way, just to find very specific use case, like, for example, training and the computing of the stochastic gradient descent for the machine learning, and put it in the FPGA, yes. And that the University of Zurich, the guys from the University of Zurich, just got the approach that let's make the very specialized design and put it in the FPGA, try to put it in the FPGA. And what they achieve, yes. For example, the training time for the same quality was increased by 10 times, yes. Using that FPGA, yes, in the specific problem, yes. We're also working with the same guys, but unfortunately I have no information how they use this, and this is one of the examples, yes, how it could be used, yes. Another way to use of the FPGA is, just let me present this one. This is this part, yes. We call this HSSI. This is the high-speed serial interface, yes. We are Intel are implementing here, working on the HSSI. This is just set of the 16 parallel links, which you could connect anything. We have currently the PCI card which connects the Ethernet here, yes, normal Ethernet. So we can make the FPGA as a card HSS. We can make this FPGA working as the Ethernet card, yes, very closely connected to the CPU, yes, making some acceleration here, yes. For example, maybe you are aware that Microsoft also using the Altera design made a product of the Catapult, yes. They use very similar approach here. They connecting, they accelerate, they created a mesh of the accelerators, yes, for the parallel computing, not using the software framework and the NIC connected somewhere in the through the PCI, but just connected to the FPGA, yes. And they had a very good result, yes. They can, for example, scan the Wikipedia in seconds, yes, using that approach. Another way of the looking for the solution, yes, how to use the FPGA, we also look into the limited precision arithmetic inside of the FPGA, yes, what the guys from the Hasler just said. Yes. So we see that, for example, for the machine learning, yes, we observe that we see the researchers of the people that, for example, thanks to the limited arithmetic, for example, the size of the model for the machine learning could be decreased by 500 times. Yes, this is the Carnegie Mellon University's. This architecture calls the QuizNet. Yes, that it is that also the very good point to finding the solution. I am that architect, solution architect, and that my job is to make it research. Yes, and I'm also responsible. Sorry, it's not. It's for the Hardware Acceleration Research Program. This is the global program which from Intel to make possible to connect the university and research centers to our hardware and to finding and making the research together with Intel and the algorithms. We have two sites, two hosts. When we have the platform, you can see that we connect the university over the world. And most of the participants work remotely, yes. It works that way, and Intel hosts a training to the accepted university, yes. We are going to this university, or this university is just going to Intel site and make a trainings from Intel how to use it efficiently, yes. What we are interested is, we are interested in the application research, with the algorithm research, architecture research, programming language research. That it is that our job from the business perspective, because Intel is a company making a business, is to increase adoption of the FPGA solution to the people. Yes, we don't know yet how to use it efficiently. Yes, we have some signals. Yes. And we are asking you as developers and researchers, yes, to help us and making the design better, yes, to get better results and get better researchers to increase the knowledge, yes, how we can use this, yes. So I'm not what the time is. It's
10 minutes.
Yeah. So you are invited to join the Hardware Acceleration Research Program. Here on this presentation there is an email address when you can set your application. Every 3 months we are making the research and we accepting the research proposals, and this is that offer from Intel to you as researchers. Yes, that. Well, it is the area where we can collaborate together, yes.
So, thank you very much for the talk.
Thank you very much, guys. That's good. So, at the very last sentences, this is what we were fighting for 2 years. Okay, so I'm very happy that you are the first guy from Intel who really put the things on the table. So we will definitely want to sign up for this thing, and it's really very important because this is what exactly we would like to find this connection. So maybe you can tell to your.
I am responsible in the Europe for that program.
That's
Yes.
perfect. You should tell to your bosses because we've already contacted some of the upper guys that how to contact it, but it took 1 year to reach you. So the inner communication should be improved a bit. So anyhow, will you please go back to the slide with this extra output of the boards, which was the design of FPGA on
Yes.
something. And this one. So what's the bandwidth of this HSSI? So what we can put there?
We can achieving that using the 10 links 100 gigabits per second. So
100 gigabits.
Using 10 links, we have 60 links.
And what's the? You mentioned this UPI, the new version of the inner
Yes,
communication.
because this is the color. This is QPI is called on the Brawler. It was really a pilot. Yes, it was not a product. Yes, we provided to some customers as a pilot. This was, I think, a few hundred boards. Today we have the Skylake. Yes, and we have even the plans to extend this to another processors. Yes. So.
And can you actually feed the FPGA registers with this 100 gigabits per second?
It depends on your application. Yes, currently we have the design depending on what you have inside of these accelerators. Yes, and what do you want to do with this 100 gigabits per second? Yes, that without the big problems, we have Ethernet MAC here. Yes. We are working with some customers to, for example, connecting here another link, yes, because we are. This is just the link, serial link to the FPGA. Yes, you could connect this You connect this everything what you can just making the processing inside of the accelerators. Yes. As part of the design in Intel, we provide. Some interfaces because in this model you do not work directly with the pins of the FPGAs. Yes, as Intel, this is product designed for the data center, we provide some security framework. Yes, we call this blue bit strip. And so your design, what you're creating, you are creating design to the sound environment. You have some interface here. You do not working directly with this QPI or the PCI. We have here the interface which is called the CCI, the cache coherent interface. And we have here the part of the implementation which is connecting to the HSSI. So we're providing you environment where you can put your design, which is the well-defined. Yes, it is, and thanks to this, you can, for example, thanks to this, whatever the part of the FPGA you are doing. Yes, we always changing, for example, this part or this part. Yes, on this level. Yes, so fixing back, your design stays exactly the same. Yes, because you are using the same API. This is not working as a normal FPGA. Yes, you have some internal API from the hardware point of view. Yes, this is Intel job to provide the connectivity to the real CPU and the links here. Yes, and to the HSSI. Yes.
I think from our point of view, this will be the key because what we are exactly using now the FPGAs to collect data from the front ends of the detector parts from the huge experimental facilities, and then take it to the FPGA, make a very quick arithmetic stuff with it, and then push it forward. So this kind of technology would be extremely useful for us. So is it really exist in this stage?
Yes, but I think depending on the customer level, yes, we have the some release process, but I think I don't want to say about the some roadmaps of Intel, yes. But we are planning to go wider, for example, in the next year. Yes, so that it is. I am not the marketing guy or the salesman. Yes, that I am the architect. Yes. So.
No, we are asking this if it would be available, this kind of device ready to test. We have things to do with this immediately. If it's in the future phase, we can figure out what should be the importance from our side.
Yeah, we are very close in that, depending on the, for example, who are working to, yes, which is our partner, yes, when you are talking with, for example, with some large partners, yes, and you can ask this environment even now from the partners, yes, through our channels and the partners, yes, so.
Another question there?
Yeah, I actually wanted to ask, because of course you want to hide all this so that it's clear to the user, but on the very core hardware level, how is this actually working? So what do I see from the CPU? Some IO registers or new instruction sets, or what do I see?
You see the memory, MMIO, and inside of the accelerators we implementing that, for example, the DMS engine, yes. And from the CPU, and this is the Q level. This is the Q level design, but this is not the part of this framework. This is part of this accelerator, so you can choose, for example, whatever Q do you want to use. But we are working and creating, for example, some to make writing a software more similar, because that. The problem of the performance is not only in the FPGA. This is also in the software. Yes, how to push the data efficiently from the software to hardware and back. Yes, and we are working very much on the VirtIO design. For example, to have drivers for free. For example, to see to the software, on the software level, to implement here the VirtIO implementation and to make to the Xeon software that some VirtIO queues. When you can access like that, for example, VirtIO net from the virtual machine, you have the drivers. And you have in the Linux kernel, whatever, in the user space, and you can use this for that way, yes.
But you see the full FPGA as memory?
No.
Only some lines of it, or?
No. We have no implementation for the home agent. Yes, this is not. We have some very small part visible as registers. We call this MMIO. So you
how much is this? It's like
yeah,
100 bits or?
This is, I think, that a few thousand registers. Yes, yeah, but it is not for the data. This is for the doorbell, for example. Yes, processing doorbell. Yes, so for example, in the software, in our software, which is called, let me present this one, which is software which is called the accelerator abstraction layer, IAL. We have a kernel driver when you can register today, and this kernel driver today will pin you memory, and you can access sharing this memory through the kernel. Yes. In the future version, we are working on the method of do not pinning the memory. Yes? So working on to make that available memory to make the host memory available to the older memory, not only the pin memory or registered memory, but all the memory provided to the FPGA. Yes, it is not ready yet. We are working on this one. And to use also the virtual addresses, yes, because we have the need to move making the physical to virtual address space, yes, conversion.
Okay, I see that there is more interest in this topic, and everybody's imagination and creativity is passing, but we don't have time right now. Just one more further question. But I would advise that we will continue this discussion in the lunch break, which is after the next talk. But one last question from Heather.
You mentioned that you are still looking for the killer application for
Yes.
FPGAs. Why image processing and machine learning is not the killer application?
Really, as an architect, yes, we are considering doing such research to check how it will work. Yes, the problem is that today we have only the accelerator for this one, because this accelerator for the NPL-DNN, this is just some acceleration of the floating, yes, in some specific CAFE format, yes. It's unfortunately that, for example, when you have the machine learning layers, yes, you must making the accelerating of the floats even in the efficient way is not good, because you at every layer you must copy the tons of data between the CPU and the GPU and the FPGA, yes, and vice versa, yes. So. And that we are looking for maybe some experiments, yes, how to put orders, for example, classification inside of FPGA, yes, maybe this is that, because we have small data and input and small data and output, yes, but this is the big research before us, for example, how to limit the model, yes, size of the model, yes. Inside of the FPGA, in the current model, we have about 4 megabytes of the memory available to the user today. And in the next version, in the next generation, we have attached the memory. We have attached memory here to the accelerator, which will be more bigger. That will be then going in the gigabytes. Because today this is the 4 megabytes. This is another problem what we have with the, for example, accelerating workloads like the machine learning. Yes. So because the model is so big that we couldn't fit it inside of the FPGA. Yes. The first we must make research how to compress this, and next we can think about that. But I think that people are looking at these things, because this is not the only FPGA problem.
Okay, let's thank the speaker again.